This conference will now be recorded.
Very good evening, students. We were discussing electrostatic part, and we had already discussed Coulomb force and related numerical problems. So today we will be learning, and also we have discussed electric field. Today we'll be discussing electric potential energy and electric potential relation between them. So let us start our discussions on this topic. So as you know, in 11th standard we have learned there are two types of energies: mechanical energy, one is kinetic energy, and another one is potential energy. So you might remember, when we talk about potential energy, we need to know that the force must be conservative in nature. Then only we'll be able to define potential energy. So potential energy could be defined only for potential energy could be defined only for conservative force field. Conservative force field. So we have so far discussed about conservative force field is the gravitational. Gravitational force field is one conservative force field. And you know, this electric field, see, electric force between two charges is directly proportional to the product of the charges, and the force is, see, suppose there are two charges, q1 and this is q2. Let us take for the time being positive charges. So, and see, the force always acts along the line joining them. Okay, force always acts along the line joining them. That means force is acting or directing towards a point or away from a point, right? Towards a point or away from a point. And also it depends on the inverse square of their separation. See, Coulomb force is inversely proportional to the square of the distance, right? So square of the separation. So these two things are similar to the gravitational force field. Okay, gravitational force. So gravitational force also acts along the line joining them, and there also we have seen the force was varying with the separation between the masses. How it was varying? Force of gravity, it was also varying inverse square of their separation. Okay, so electric force and the gravitational force, they are same or similar in nature. Okay, I can say just like gravitational force. Okay, or conservative force. Conservative force. Okay, just as gravitational potential energy, then we could also define potential energy for the electrostatic field, or in other words, since gravitational force and electrostatic force both are conservative in nature, and we have seen in case of gravitation we had defined gravitational potential energy U, gravitational potential energy U. So here also electric field must be associated with some electric potential energy function, that is U. Okay, so that we can expect, isn't it? So from that perspective, or from that analogy, we can think of potential energy function U associated with electric field as well. Okay, so when a force F acts on a particle that moves from A to B, some path A to B, the work done given by, in case of electric field I am talking about here. So in case of electric field, if suppose there is a particle situated at A within the electric field created by some charge particle, and this charge particle is moving from A to B. So what will be the work done, and how do we express that work done? So that work done could be expressed as W A to B and how do we express it? We express this in terms of integration A to B F dot dr. R is the distance I'm taking, distance of separation. Okay, so look, A to excuse me, yes, there was a power failure, so there was some network issue. We are back, so let us resume our discussion. So what we were discussing, that in an electric field, if a charge particle, or simply in case of, see, in case of any force field F, suppose there is a force F, if a charge particle, if a particle moves from one place to another A to B, so generally we define work done in this way, right? So F dot dr, so it will be F cos theta, and dr, here upper limit is B. So this cos theta, dr is what? Dr is the separation between the charges, or sorry, separation between the points A and B. or in this case we can just take very infinitesimally small distance while going through this path. So it is moving suppose by dr separation. So like that we are just, because uniform may not be uh, like electric field may not be uniform every time, so in those cases we can actually go with integration. So this, so what we get is this f cos theta dr, that is the displacement. So dr is the displacement, okay, and f is the force, and cos theta is the, theta is the angle between this dr displacement and the force existing here. Okay, so this is cos theta. So here dr is displacement. This is in general, okay, and force is the, f is the force, sorry, f is the force, okay, and theta is the angle between them. So here this force is actually conservative force, and angle theta, theta is the angle between f and dr. Okay, now let us go to the next page. Now if this force is, if this force, if f is conservative in nature, then see this point A and this point is B. So at this point there must be some potential, okay. So while particle is moving from a point A to the other point B, so it is actually moving from a potential, a place where potential is u here, ua, and here potential is ub. So what is the difference in the potential between these 2 points? Difference in potential, this is difference in potential, in potential, difference in potential, ub minus ua. So this is the difference in potential, okay, and this difference in potential could be related or correlated to work done. See, work done we have seen, work done from A to B, work done from A to B, we have seen already, and this could be related to the potential energy, C U A minus UB, and if I take this UB minus UA, so this is minus delta U. So we can actually write work done A to B will be always change in the potential energy between the two positions along with minus sign. You might be thinking, what does this mean? Why do we so bother about this relation between work done and potential energy change in the potential energy function? You might be worried about this, right? Let me tell you why we are, or in other words, what we are exactly trying to say. Let me uh, take a simple example. Suppose I have, in case of gravity, let us go with the gravity. I have a ball of mass m, okay? Then if we lift this ball, if we lift this ball, I'm sorry, if we lift this ball like this, okay, so we are actually, G is acting this way, so work done, see if the displacement is some, so force is actually mg on it, so mgh, this is the work done by the, this is with the minus sign, this is work done, okay? Mgh is the work done by the gravity, work done by gravity, done by gravity. So this is work done by gravity. But what is the change in potential energy here? See here, potential energy UA was 0, but here it is UB some. So here potential energy U, change in potential energy is positive mgh. So change in potential energy is positive. So what I'm trying to say is that if the work done by the field is negative, then the potential energy change or potential energy increases. We can say potential energy change is positive. That means potential energy increases. Okay, I'll write the corollary to this. And with electric field also, we can just see this thing, see this example. See, when the work done is positive, when WA to B is positive, then delta U is negative. Is negative, and the potential energy decreases, and the potential energy decreases. So whenever work done by a conservative force is positive, the potential energy of the system decreases, or vice versa. So I can just write this in other words. Whenever work done by a conservative force is positive, potential energy decreases. Decreases, or vice versa. Okay, let us go with a certain example for this. Okay, so let us take an example. A uniform electric field, a uniform electric field E0 is directed along positive y direction. Find the change in electric potential energy find the change in electric potential energy of a positive test charge Q0 when it is displaced in this field from along y-axis. Okay, I'll explain the problem once again. Look here. Suppose the electric field is acting in this way. Say E0, constant electric field E0 is acting along the y-axis. So this is 0, 0 origin. Say this is y. This way it is positive axis, and a charge particle is taken from some position y is equal to a to a somewhere here. So it is taken from a to 2a, charge particle q0. So what will be the change in the potential energy? So how to solve this problem? We know already how to do that. So we know work done, we have to find out. So first of all, we need to find out work done. See, work done here, suppose I say this point is A and this point is B. So work done while going from A to B. So that we know that F cos of theta and dr is the displacement, and we need to take the integration limit A to B. Okay, so in this case, let us first find out what is the force. So we know the force on a charge due to electric field is Q0 into E0 here, and here E0 is a uniform electric field, so this is the constant force. So this is a constant force. So, and you know, this case, the displacement is happening along the y-axis itself, and the electric field, see, on positive charge particle, electric field actually just attract the positive charge particle towards the electric field direction itself. So direction of the force and displacement is along the same direction, so theta is 0 here, 0 degree. So let us rewrite this. A to B, F is what? Q0 E0, and cos theta is 0. So cos theta is 0 means cos theta is equal to 1, and dr is actually dy here. Okay, dy. All right, so look here what we do. So A to B is equal to yi to yf. This is actually yi to yf. Force is q0 epsilon, sorry, e0, that is the force, and this is dy. So Q0 E0 dy means YF minus Y initial. Okay, so this is Q0 E0, YF is 2A minus A, simply A, Q0 E0, Q0 E0 and A. So this will be the force. Okay, so this is the force, as you can understand that. Sorry, this is the work done. But how is it related to change in the potential energy? So it is related to change in the potential energy minus du. So this is Q0 E0A. So here we can see as the work done is positive, work done. So here work done by the electric force or electric field. Electric force, let us say, electric force is positive, and hence the potential energy is decreasing. Okay, so this is how, or this is the thing we just wanted to like say or understand in the previous corollary, as I had written here. When work done is positive, delta U is negative, that means the potential energy decreases. So this happens for any kind of force, conservative force field, whether it is elastic force field or gravitational force field or electrostatic force field, because all are conservative in nature. Now what we'll do, we'll just go for calculating electric potential energy due to two charges. Okay, electric potential energy okay, so electric potential energy of two charges. The idea of electric potential energy is not restricted to the special case, to the special case of uniform electric field. See, in the previous case, work done and all this case we have discussed. See this, here we had uniform electric field or constant electric field. Okay, but when we talk about potential energy of two charges, so that will not be, their electric field will not be constant, or the force will not be constant or uniform. Okay, electric field will be varying, as you know. See, if I just take or if I just calculate work done on a charge particle Q0 which is moving in a non-uniform electric field caused by another stationary single charges Q. So suppose this is a single charge Q. Okay, and as you know by now that electric field, a point charge, this is say positive point charge, it will create an electric field around it, isn't it? So if I just take this point, it's A, and this point is B. Suppose another charge particle Q0 is somewhere here with a positive sign, say. and the separation between these two charges now R. Okay, so we want to calculate the electric potential energy due to two charge system. Okay, so this charge system, so suppose if I just move this q0 from A to B, what will be the work done? We need to first find out. Okay, so if we want to calculate the work done for displacing this q0 charge from A to B, what we need to know? See, we need to do the integration A to B f cos theta into dr. So dr is the displacement, right? So here, what is the force? First of all, force is Coulomb force here. So this is Coulomb force. You know what it is? q0 by 4 pi epsilon naught r square. Okay, this is the force here. Okay, so work done, if we write here cos theta, since it is like Coulomb force will be acting along the direction, like along the line of joining. So let us take this cos theta is equal to 1, so A to B, so F is q0 by 4 pi epsilon naught r square. This is the force and this is dr. Now if we integrate it, what we get, we get, see, we'll get 1 by, see, q0 by 4 pi epsilon naught. Let me keep this part outside this bracket. So this will be minus 1 by r A to B with this limit. See, if we write in this way, 4 pi epsilon naught, and this I can write 1 over A minus 1 over B. So this is the potential, sorry, work done. This is the work done in bringing the charge q0 from A to B and within the electric field created by this positive charge q. All right, now if we want to correlate this work done A to B with the change in potential energy, that we have to write delta U like this, or yes, or in other words, we can write this UB minus UA like this with the minus sign over here. Okay, so UB, so if we write this, see work done, so UB minus UA will be how much? This will be minus WAB, A to B. This is then, see, this is q0 by 4 pi epsilon naught, and here it is 1 over A minus 1 over B. So if we just resolve this minus here, one over B minus 1 over A. So this is actually UB minus UA, or delta U, change in potential energy. Okay, this is okay so far. So what we are trying to do is actually we need to actually find out potential energy with respect to, so with respect to some reference. Potential energy is always calculated. Potential energy is always calculated with respect to some reference. Some reference. So what will be the reference? Reference is chosen in such a way that the potential energy of the reference will be 0. So this is the reference in general you choose. In case of gravitational potential energy calculation, we have taken the earth surface to be reference where the potential energy has been taken at 0. As it goes up, the potential energy increases. Okay, so U increases. All right. So similarly, in case of electric field or electric potential energy, see what we have here. Electric potential energy UB minus UA is equal to Q0 by 4 pi epsilon naught. This is 1 by A minus, sorry, 1 by B minus 1 by A. This is what we have seen. So the potential energy is a reference. If I want to make this place A, point A as reference, then this point A, if we want to make A point as reference, then UA must be 0. Potential energy at A must be 0. When is it possible? It is only when, and it is possible. It is possible. Sorry. It is possible only when A tending to infinity. That means when there will be no effect of charge Q on Q0. So if it is at infinite distance Q0, so there is no effect. This field, electric field, will not be affecting anyway on this Q0, and that happens only when R is infinity. Okay, because electric field, we know electric field is inversely proportional to the square of the separation. So if R is infinite, then electric field also will be 0 at infinite distance. So therefore, the reference in case of electrostatic force field is taken at infinity. In case of gravitational force field also, the reference has been taken at infinity, where there is no attraction felt by one mass by the other. Okay, so in this case also, this point, if I just keep at infinity, then look how the potential energy term could be written. See here, UB minus 0 then. Okay, or let us write this is infinity, U infinity is equal to Q0 Q0 divided by 4 pi epsilon naught, and this is 1 over A, sorry, 1 over B 1 over B minus 1 over infinity, that is 0 only. So this is also 0, potential energy 0. So UB can be written as Q0 by 4 pi epsilon naught 1 over B. Okay, in general, electric field, so this is actually written, so UR, let me write this as UR, because it is a function of the separation, 4 pi epsilon naught R. This is general formula for potential energy term. Okay, potential energy due to two charges. Okay, this is general formula for potential energy. Okay, sorry, general formula. for calculating potential energy. Okay, so this was one point. So this expression for the electric potential of 2 point charges kept at a separation of r. In this expression, the charges q and q0 are to be substituted with sign. If both are positive, then it is positive. If both, as one among them is negative, so I'll write it is. So this is positive. Okay, if q and q0 both are positive, both are positive. Okay, and u r, this is negative if one among or one of the two charge is negative. Okay, so this is the potential energy. Okay, now see here, potential energy does not depend on the point where we are calculating the potential energy in the electric field. Okay, it depends on the separation. Okay, it depends on the separation. So we emphasize that the potential energy u so u given by this expression conservative. Okay, so this is an interaction, actually interaction between the two charges. If the distance between the charges is changed, then the potential energy also will be changing. Okay, but here see, potential energy, while calculating the potential energy, it doesn't matter which charge was fixed and which charge was moved. If I would have said that q0 charge is there and q is moved from one place to, or displaced from one place to another, so that will not make any difference in the expression. Okay, so therefore we won't talk much about potential. Say we will not say this phrase that the electric potential energy of a point charge. We will not say electric potential energy of a point charge, because this electric potential energy, whether this is fixed or this is fixed, doesn't matter. If we cannot say electric potential energy due to q or electric potential energy due to q0, because electric potential energy due to q, electric potential energy due to q0 are the same. Okay, if q0 is displaced in the field created by q, the expression will be this. If the q is displaced from one place to another in the field created by q0, the expression will be the same. So we would not say the phrase electric field potential energy due to a charge. We'll say electric potential energy. That's enough. Okay, now electric potential energy of a system of charges. How do we write electric potential energy? Potential energy due to a system of charges. Okay, so I'll just write it directly. See, it could be written in terms of summation. Divided by Rij. Okay, in this case, I must be less than J. Okay, what does this mean? So you know this is summation sign, summation. Okay, I'll just let you know this thing. See, if I just take I and J equal, then what happens? Q is, see, suppose I have two charges, Q1 and Q2. So if I write Q11, that means what? Sorry, yes, this I can write Ij, Uij. So U11, that means the interaction between the charge and itself. Okay, so interaction between itself is, it is not possible. So interaction with self is not possible. Interaction has to be with some other charge particles. So interaction, so that's why this term is not there in the expression. Okay, I'll just give you one example that will make you clear, that will make your idea clear about this expression. Suppose I have 5 charges. If I have 5 charges, how to write down this expression? Okay, how to write down this expression? Let me tell you, if I have some 4 charges, say like this, there are 4 charges. So Q1, then Q2, Q3, and Q4. So due to this system of charges, how do we write this expression elaborately? Or simply I can write, see, I can write this U as, see, when I write this as 2, or let us start with 4. So Q4. So it will be less than that, that is Q3, divided by, so this I have taken 4, this I have taken 3. So this will be 4B. That means the separation between charge 4 and 3, this one. Okay, plus if I write this 3, then it must be 2, and this is 3, 2. Then Q2, then this must be Q1, less than that, and this will be 2, 1. So can I write 1, 1 or 2, 2, 3, 3 like that? No, these are the terms. So there will be these terms. Okay, actually not only this, I'm sorry, there will be few more terms. So like this, suppose this combination, okay, these terms also will be there. Okay, so those combinations also will be there. Potential energy, I'm sorry, let me just complete it. Plus, so if I write, okay, I would have, okay, let me go with other terms. So we have 4, 3. So 4, with 4 I can have another 2 combinations, 4, 2 and 4, 1. So these combinations also will be there. So 4, 2, here 4, 2. 4 1 here, 4 1. Then this with 3 and 2 also will be there. 3 2 I have already written. 3 I have already written. Okay, so these are already done. So with this Q3, with Q3 I can have 2 and 1. So 2 I have written already. So with 1 also will be there. Q1 by R3 1. Now 1 2 we have written already. So how many terms we are getting? 1 2 3 4 5 6. So I think 6 terms will be there. Yeah, there will be 6 terms like this. See, how do you know how many terms will be there? See, Q1 2, sorry, 1 2. Then I have Q2 3, Q2 4. Okay, and Q1 3 1 4, Q1 3 1 4 or 4 1, whatever you say. So this will be there. So all possible combinations or interactions will be there. That means Q3 can interact with 2, it can interact with 1, it can interact with 4. Okay, then say Q4 can interact with this, Q4 interact with this, Q4 interact with this. So this is how. Okay, now, but here always here I have taken all the charges positive. So you have to take the charges with positive. Now how can you be sure that I have calculated or I have written all the terms? So to check that, there is, say, number of terms will be number of terms. Here I'm writing number of terms. How do we calculate? We calculate n into n minus 1 by 2. Like, see, in this case, how many terms, how do we find out? We see what is the number, maximum number here. The maximum number was 4. Okay, like I in the sense, how many particle is actually constituting the system here? How many particle? N is the number of particles constituting the system. So there are 4 particles constituting the system. So I can write 4 here. 4 minus 1 is 3 divided by 2. So this will be, there will be 6 terms. So you can be sure with this formula, n into n minus 1 divided by 2. Okay, so this is the formula, or this is the way how you can calculate electric potential energy due to a system of charges. Okay, now we'll take upon a simple example related to this calculation of electric potential energy, and then we'll conclude the session. So 4 charges, suppose 4 charges, I'm just not writing the words, I'm just giving you the figure. So 4 charges are kept on the vertices of a square of 1 meter. So this is square of 1 meter side 1 meter. Okay, so there are 4 charges here, Q1, then Q2 here, Q3 here, excuse me, so Q4 here, and see Q1 is given as 1 microcoulomb, Q2 is given as 2 microcoulomb, Q3 is given as minus 3 microcoulomb, Q4 is given as 4 microcoulomb. So so how many terms will be there? There will be 6 terms, as you know. And how to calculate that? See, first of all, we need to find out the distances. In this case, see, if I go side by side, 1 2, see R1 2, then R2 3, then R3 4 or 4 3, whatever you say, and R4 1. All this side by side. So these are 1 meter, 1 meter, 1 meter. So these are 1 meter. Okay. But what about these distances? So this is suppose R 1 3. I'm saying 1 3, and this is this diagonal R 4 2 or 2 4, whatever. So these are actually R1 3 or R2 4, say. So this will be root over 2 into A, right? Root over 2 into A. Root over 2 into A is, see, A is this. A means side of the square. So A is 1 meter. So this is root over 2 meter. Okay. So we have already found out the distances, and we'll calculate writing the terms, right? We have already written for 4 terms, like 4 charges. Let us just directly write here. So we know this 1 2. See, we have to actually write all the. Let us just skip this 1 by 4 pi epsilon not this out. Okay, we'll write. See, we'll write 1 2 1 2. Okay, potential energy due to this between these two. So that means, sorry, this is q1 q2 q1 q2 by r12, and due to, for one we'll write directly q1 q3. That will serve q1 and q3, and q3 q1 are the same. So this will r13. So with 1 2 interactions are already done. Okay, these 2 interactions are done. With 2 I'm not going to write q2 1 because that is the same. So with 2 I'll write 2 3 r23 and r24 2 q4. So r24. Now with 3 I have this and this. Okay, I have already written q2 q3. I have written already q1 q3. So I have only term remaining q3 and q4. q3 and q4. Okay, so this will be 3 4. How many terms we have got? 1 2 1 2 3 4 5. One more term is remaining, that is 4 2 or 2 4. All right, so that is already done. What is remaining? 1 4. 1 4 did I write? No, we have not written 1 4. Okay, we'll write 1 4 or 4 1. q4 q1. So this will be 4 1. So 3 and 3, 6 terms will be there because 4 charges are there. So now here, if we write q1 and q2, I'll just erase and write here itself. Otherwise, we have to rewrite this in the other page. So q1 is 1 microcoulomb. I'm writing here. So 1 microcoulomb, and so 1 to 1 into 2 microcoulomb 10 to the power minus 6. That could be taken here, 10 to the power minus 6 here. Okay. In fact, this term also will just write down. See, u is equal to 1 by 4 pi epsilon 0 means 9 into 10 to the power 9 we are taking, and 10 to the power minus 6 we are writing due to microcoulomb for each of them. So 1 to r12 is the distance. So what is that? R12, so that is 1 meter. So let us write this divided by 1. Okay. Similarly, q1 and q3. So q1 this is 3. So this will be with a minus sign. 1 into 3, 1 into 3, and q1 q3, this distance will be root 2. meter. Okay. Now Q2, Q3, this distance will be anyway 1 meter, 1 meter, and 2, 3. So this will be 6 minus 6 here with the minus sign. 2 is 2 microcoulomb, and this is 3. Okay. 2, 4, 2, 4 or 4, 2. This distance is root 2. So I will write this here. 2, 4. 4 is positive, 2 is again positive, so this will be 2 into 4, 2 into 4. So what about 3, 4? 3 is negative anyway, 4. So this will be with a negative sign. 3 and 4. This is negative sign. And again, this is 3, 4 is anyway, that is 1 meter. What about 4, 1? 4, 1 also. So you can write 1 and 4. These are positive, so 1 into 4 or 4 into 1. This is 1 meter. So look here. If we could do the proper calculation and write the answer, what it will be. So this is, since it is a work done, we had seen that we had calculated through work done, so it will be in terms of joule, and you know what will be the result. The result will be minus 7.6 into 10 to the power minus 2 joule. This will be actually the answer for this system. Okay, like potential energy for this system. So this is how we have to take for many particles. We have to take all the terms one by one, and patiently we have to write down the terms so that you don't forget or don't leave any pair. So this is the answer for this particular question. We have such many problems. We can do it in the next classes. So today we'll stop it here, and thank you for your patience. Bye for today.